voir l'écran du coup, avec Victor qui nous parlait de Petri.
Merci. Ok, je vais faire mon exposé en anglais parce qu'il y a plein de notions et c'est plus rapide. Première, vous pouvez poser les questions en français, pas de problème. Mon exposé sera antipédagogique, mais j'espère pas catastrophique. Ok, donc je vais vous parler d'un travail en commun avec Jérémy Chalopin qui est là. Et il est basé sur un papier apparu dans ICM Transaction Computational Logic. And so I switched to English. And the main goal of the talk to explain you a bijection between one safe Petri nets and the special cube complexes, which are completely different areas of research. And essentially, this is on the level of bijection between the event structures associated to derived from special cube complexes and also from unfolding of one safe Petri nets. And this can be viewed as a positive answer to a conjecture which we disproved of Thiagarajan, which event structure occurs as unfoldings of one safe Petri nets. So, and the vocabulary is like I have to speak about, explain notions from concurrency theory, like Petri net, event structure, unfolding, domain, trace, Mazurkiewicz traces, and geometric group theory, which are non-positively curved and cut-zero cube complexes, special cube complexes, universal cover, hyperplanes, and metric graph theory, which is median graphs and gated sets. By the way, to not forget, if the nicest cut-zero cube complex of median graph in this room is on the T-shirt of Dmitry Sokolov. Please, you can show it. Yes. This gives you. And there is a bijection between the three structures when you have the same language. Event correspond to hyperplanes or in the cut-zero cube complexes and to theta classes in median graphs. And what is an event structure? After Nielsen, Plotkin, and Winskell, it's a triplet of you have a set E of events. Then you have a partial order, binary relation of precedence, and you have a binary conflict. Binary conflict is a symmetric conflict. If two events are in conflict, A and is in conflict with B, B is with A, etc. And then you have two axioms. One is saying that if you have an event, all events which precede it, also this set is finite. And the second is we call vendetta axiom, is saying that the conflict is inherited, that if you have two events which are in conflict, all events which come after that are in conflict with the second event. And you can see that, in fact, why this is in concurrency theory, because if you take the complement of the pairs which are not in precedence or in conflict, then they are called concurrent. And the concurrency comes from here. And we denote the concurrent events in this way. And then one important, maybe for definition, is a minimal conflict. It's the first time the events are in conflict, where the conflict appears. This is a minimal conflict. And here I have a small example. You have 6 events. The precedence relation is in black. The minimal conflict is dotted, and here is drawn. Okay. And an important notion for us is the notion of a configuration. And the configuration is a subset of events which are downward closed. So it's a subset of events which contain the history of all events. And second is conflict-free. There are no conflicts between events. Yeah? This is a definition of a configuration. And then the domain of the event structure is a set of all configurations ordered by inclusion. And if you want to see from the graph point, you just take the Hasse diagram of this poset of configurations. For example, here, this one is a domain of the event structure which I drew before. You see this is an empty set. It's a configuration. But here also you see A1, A2, B1 until B3. It's also a configuration. And the domain is important for us because we are specialists in domains and not in event structure or Petri nets. And one important notion is a labeled event structure. So you have an event structure and you label the events with the letters from one finite alphabet. And then a nice labeling is a labeling in such a way that two events which are concurrent or in minimal conflicts are labeled differently. This is a notion of a nice labeling. And essentially you can also see the nice labeling as a coloring of edges of the Hasse diagram with the condition that whenever you see a square, the opposite edges of the square should be labeled in the same color, with the same color. And if you have two outgoing edges in the Hasse diagram, they should be labeled differently. This is a determinism and concurrence. Opposite the same color and the other two should be different. Yeah. It's clear? No, I said. No. Okay, don't look at my hands, look at my definitions, okay? They are correct. My hands are telling something else. Okay, and now we speak about this unknown object for us, which is one safe Petri net. What is a one safe Petri net? It's essentially a bipartite graph. You have S, a set of places, and sigma is a set of transitions, and you have a flow relation, which is just edges of the arcs between the two parts, between places and transitions. Yeah, and then you have a initial marking. So you have a subset of places having token. So they are holding tokens. This is the initial marking M0. And then for some vertex of this bipartite graph, you denote by V in this way the in-going and the outgoing arcs. Or this is the notation I will use later. And then the marking. So you have an initial marking, and then you have a process which is from one initial marking you can go to another marking, etc. And then what is a general marking? This is just a subset of tokens in the places. Yeah, this is one safe because usually in Petri nets each place can hold many tokens. But in one safe Petri nets, each place can take have either 0 or 1 tokens. And now a marking is reachable. Marking is reachable if you can activate a sequence of tokens and to go from the initial marking to the given marking. And to fire this is the important definition, the firing rule. Then a transition A from fire, you can fire transition A when you are in marking M, and you'll go to the marking M prime if the following conditions are satisfied. This means the first condition means that all the in edges, all the places having in edges to the action hold tokens. This is the first condition. This is the second condition, which is a little bit technical. And if the two conditions are satisfied, then you go from marking M to M prime, and this M prime has this form. So you remove the tokens from the in, and then you put tokens to out. And this is an example, but I make an error in this example. So you have this Petri net, and imagine that you have tokens on P1 and P2, and then you fire this transition, and when you fire this transition, then you will get. I make some error. I think that an error is that you have arcs here. Yeah, I think no. I think it's okay. No, here I make an error. Yeah, I make an error here.
T2 and 3 incoming edge.
Okay, yeah, C2, yeah, should have 3, yeah, should be here.
No.
No?
If you want to fire T2, you should have a token.
Okay. Okay, and what happened that when you fire once, you get this position, but here you can fire either T1 or T3. And then again, you develop and you continue. And in fact, is what you get is like the unfolding. And this unfolding is shown here in a more correct way. So you have one safe Petri net with initial marking in these two places. And then you see that you have 3 transitions, A, X, and B. And then when you start to develop, to simulate this Petri net, then essentially you see that you cannot activate at the same time A and B, fire A and B, because they use the same resource. There is the same input. Therefore, A and X, not A and B, but A and X. And this means that, in fact, you will have a kind of conflict because they share the same resources. And then you can unfold, and this is called the unfolding, event structure unfolding of the one safe Petri net starting from the initial marking. This is not the precise definition. I will give it you later, the precise definition, but this is just a feeling that you can go from the one safe Petri net to an event structure where you develop the transition can occur many times, and you have a conflict because you have a transition which you use the same resources, etc. And if you look at the domain of this event structure, then you see this domain is this one. Yeah, it is colored because you label essentially the events by the letters of the transition. So you have 3 colors, A, X, and B. And this is a haired grid. And if you forget now the colors, this is a...
Sorry, can I
yeah.
So why do you get a nice labeling? So you have all the transitions in the Petri nets have different labels? Or?
Yeah, we use this for, it is finite Petri net, and we use one color for each transition.
For each transition.
Yeah. And we will use this kind also for special cube complexes, etc. And now you have this. This is quite kind of regular domain. It's a regular. If you forget the colors, in fact, you have the following that you define the regularity in the following way. The future of a configuration is all configuration coming after that. It's in this poset. This is a principal filter. We call it the principal filter of the configuration. And if you look, how many isomorphism types of futures you have? We have just two. This one kind of future, haired grid everywhere. And you also have a future which is just one terminal configuration. And this is a regular. And a regular event structure is a structure for which you have just a finite number of futures, isomorphism types of futures. Yep. And now you can color also. You can label. Okay, so it's here. And in fact, Tyagarajan, and I forgot. Regular nice labeling now is a nice labeling in which you have a finite number of isomorphism type of colored, labeled features. It's clear? Regular is not labeled, and regular nice labeling, it's labeled. It's like colored graphs, but you have regularity. And Tyagarajan proved that if you take the unfolding of one safe Petri nets, then they give rise to regular, nicely labeled event structures. Yeah, and then he conjectured that.
What do you mean by unfolding?
Sorry?
What do you mean by unfolding?
Unfolding, what I said before. Unfolding is this event structure which you create from the one safe Petri net. I will define formally if I will have time at the end. So, anti-Lagrangian conjecture was that any regular event structure, in fact, admit a regular nice labeling and occur as an unfolding of a one safe Petri net. And with Jeremy, we proved that this is false. It's very false, in fact. But the conjecture is very nice. Really very nice. And in fact, this is a good question. Maybe not as a conjecture, but which event structure occur as unfoldings, and we'll try to answer this. And in fact, we work with domains. We never worked with event structure or with one safe Petri nets, but with domains. And the domains, in fact, they are median graphs, and at the same time, they are cut-zero cube complexes. And I will want to explain what they are. And you have a graph, and endowed with the distance matrix, and the median of a triplet of vertices is a vertex which is simultaneously on shortest path between each pair of vertices of the triplet. Yeah, this is a median. And the median graph is a graph in which any triplet has a unique median, a single median. And here examples are trees. And in a tree, for example, the median of a triplet is just the lowest common ancestor of V and W if you root the tree in U. And why this is called median? This comes from grids. Grids are median. And what is a median? You take a triplet and you project, and you take the middle coordinate on each coordinate, and then you take a point, a vertex, which has such coordinates. And this is a median. It's a median of triplet of numbers. Cubes are medians. Distributive lattices are medians, median graphs. And if you just take the definition, then you think, it's just ugly definition. But if you work 1 hour with median graphs, you will discover that they have plenty of cubes. Essentially, they look like this, or like the T-shirt of Dmitry. I put a lot of investment in selling your T-shirt. And one important thing in this area is this called parallelism Djokovic-Winkler relation. You say that two edges are parallel if they are opposite edges of the same square. And then you take the transitive closure of this relation theta 0. And this is called the parallelism relation of theta classes. And if you cut the middles of the edges of a theta class, you get something which is called the hyperplane in geometric group theory. Why? Why? Because, in fact, you can associate with a median graph, you can associate a cube complex, that one. Namely, you take any graphic cube and you replace by a solid cube. Yeah? And then you put a geometry inside. And you can put the L2 geometry, Euclidean geometry, inside intrinsic Euclidean geometry. And one property of such cubical complexes are that they are simply connected, in fact. And if you take hyperplanes, in the sense I defined, they cut the complex in two parts. This theta class cut your graph in two parts. And what a cube complex is drawn there. And that this cube complex satisfies nice Gromov cube condition, saying that if you have 3 cubes, here I took 3 squares, but this is enough, which pairwise intersect in edges like this. It's like walls in the room. Then they live in a room, in a 3 cube. This is a Gromov condition. And in fact, Gromov proved that just in case of cube complexes, this condition characterizes the cut-zero cubical complexes. And what are cut-zero cubical complexes? Are cubical complexes with global non-positive curvature. In fact, the modern geometry, say metric geometry, there is a nice mix of Euclidean geometry and hyperbolic geometry. And this cut-zero is just a mix of such geometries. And this means that if you take a cut-zero cube complex, then the triangles in that cube complex are thinner, geodesic triangles are thinner than in the Euclidean plane. Namely, you take 3 points and 3 geodesic in this cube complex, Euclidean geodesics. And then you take, by triangular inequality, you have a comparison triangle in the Euclidean plane. And then for any point x, you have a comparison point x prime. And the cut zero condition, or non-positive curvature condition, is saying that the distance in the space between u and x is smaller or equal than the Euclidean distance between u prime and x prime. This is a non-positive curvature condition. And the cut zero space is a geodesic space in which satisfies the non-positive curvature condition globally, everywhere. And non-positively curved space satisfy this condition locally. Locally, in each point, you have a small neighborhood which is like that. Okay. And a nice theorem by Gromov, which was in his paper, big paper was just a proposition, is that a cube complex is non-positively curved if and only if it satisfies this cube condition. And then a cube complex is if a cube complex is non-positively curved, then the universal cover of this cube complex is cut zero. This is a global thing. And the third is that a cube complex is cut zero if and only if it is simply connected and satisfies the cube condition. What is simply connected and what is universal cover, I have to explain. Simply connectivity, everybody of you knows, yeah? An object is simply connected if any cycle can be contracted, is null homotopic. You can contract in a single point. And the covering, so you see the sphere is simply connected, the torus is not. And the covering of a cube complex or topological space is a map phi from x prime to x, which is locally bijective and preserves cells. So maps square to squares, points to points, edges to edges. And you see, this is a covering map from x prime to x. And if you take the object x, there are many objects which map to x. There are many coverings. It's an infinite number of coverings. But there is a largest one, and this is called the universal cover. The universal cover is the largest cover to the object. And this universal cover is simply connected. It is unique, and it is simply connected. So you kill, taking the universal cover, you killed holes in the object. Yeah? And then, in fact, what important thing of Gromov is that if you have a cube complex which is locally non-positively curved, and then you take its universal cover, this is a globally cut zero complex. And why cut zero are important? Because in fact, there are two bijection results. The first one is that a graph is median if and only if it is a graph of a cut zero cube complex. This is one result. And the second is by Barthélemy and Constantin saying that the domain of an event structure is a median graph. And for any pointed median graph, and this for any pointed cut zero cube complex, you can realize it as a domain of an event structure. There is a bijection. And this bijection is very nice. And in fact, what is this bijection is as follows. If you have a cut zero cube complex or median graph, what is the events? The events are the theta classes or the hyperplane. The hyperplane. What is the precedence relation? One event is smaller than another one if the hyperplane of one event separate the base point v0 from another hyperplane. Look like here. What is conflict? Two events are in conflict if the hyperplanes do not cross, are disjoint, and they do not separate v0 from another one. They look like that, like in hyperbolic geometry. And finally, what is concurrency? Concurrency is just the hyperplane intersect. Yeah, this is how you get from a cut zero cube complex an event structure. Yeah.
V0 comes from the structure of the cut zero.
You can take any v0. and you get a different event structure. So this is why I was careful in saying that this is bijection, but with pointed in the second result. Okay, so this is some examples, but since my talk is anti-pedagogical, I don't give examples. Okay. And if you have a cut-zero cube complex, I said that you cut in the middle, the hyperplane cut there, and they actually have very nice property. It is the half spaces in which they cut, they are convex, and even they are gated. What means gated is that you can project any point from A to the B, and this projection point, closest, nearest point, belongs to a shortest path between X and any point of B. This is a gated property, which is useful in the proofs. But this is about the properties of domains. And you know that if you want to solve the question, which event structures come from unfoldings, are unfoldings of one safe Petri nets, then you will not get all event structures. They should be regular, and they should be more trace regular, in fact, etc. And therefore, you should look at some anomalies. And in fact, in geometric group theory, there is a beautiful paper by Haglund and Weiss, who defined the special cube complexes. And essentially, they looked not at cut zero, they look at non-positively curved cube complexes. And in this small object, the hyperplanes can have anomalies. And what are the types of anomalies they look? That you can have a self-intersection or self-intersecting hyperplane. When you will take the universal cover, this will disappear, this anomaly. Also, you can get a one-sided, a Möbius band. Then you also can get direct self-osculation, crossing two hyperplane at the same time. They can intersect, they can cross, and they can osculating, and then indirect self-osculation. And they define the special cube complex as a cube complex in which you don't have the four anomalies, but this is okay, because, okay. And this is our object. In fact, we proved that if you take such an object, a special cube complex, and you take the universal cover of this object, and you take a principal filter in this universal cover of such an object, then this is a domain of an unfolding of an event structure coming from one safe Petri net, and vice versa. This is the result. But to do this, to get it, in fact, we need to direct the special complex. A directed special cube complex is just a special cube complex in which all edges are directed, with the condition that if you take a square, the opposite edges in a square, they have the same direction. Okay? And now the first definition of a trace alphabet. What is a trace alphabet? Most of people know it better than me. You have just a finite alphabet with an independence relation, which is a binary relation, symmetric binary relation of independence. And then, okay, for the moment, I just defined this. And then, what a trace labeling of a directed special cube complex is a labeling of edges of this complex with a letter from the alphabet sigma, of the trace alphabet sigma, with a condition which say which pair of edges should give you different colors and should give you colors which are independent. And this is, first of all, if you have a square in the complex, you should have an independence pair. But if you have some independence pairs, you have such a situation, for example, you should be in a square. It's clear? They should be labeled differently, but if the labels are in an independence pair, necessarily this pair should be completed to an upward square. And then there are two other conditions for completing such paths, and also for completing upward such two edges. All time you should complete by a square whenever you are in independence relation. And our theorem 1 is saying that, in fact, a finite cube complex is special if and only if, for any admissible orientation, there exists a trace labeling of this complex. And for example, if you have this anomaly, you see, you have this kind. Why this is not special? But here you have two events which cross. So they are concurrent. They are in independence relation because they are in E, in I. And at the same time they oscillate, and they are not in I. And this will contradict this axiom, because you don't have a square. This is explain why somehow special you need to be special to get such a trace labeling. And in fact, this trace labeling, in fact, is a nice labeling, as I defined it for edges, for the universal cover. And in fact, this is irregular as well, because it comes from the universal cover of a finite object, colored finite object, and it is regular. And therefore, if you have a finite cube complex and you take its universal cover, and you take the filter, a principal filter of in the universal cover, any principal filter, this gives the domain of a good of an event structure which has a regular nice labeling. Therefore, for such objects, the Thiagarajan conjecture were true. Okay. And in fact, for the converse, when you have a special cube complex, in which way you define the independence relation, you just the two events, two hyperplane which cross give you an independence pair. This is how we prove the converse. But okay. And okay, now we have to define the special cube complex for one safe Petri net. Yeah. In fact, I have one direction of the proof that you can associate objects with one Petri nets, and they are special cube complex. Namely, I have to prove this, show this one. So you have one safe Petri net, and I want to associate to this one safe Petri net a special cube complex, square complex, in fact. The vertices are all markings. First, we take all markings, possible markings. There are 2 power n, where n is a number of transitions. And then we will look at the arc. There is an arc from M to M prime, if and only if there is a transition A, such that M prime, I forgot A. And now you take this graph, directed graph, and you just forget, and then you take forget the orientation of edges, and take the connected component of this graph with forgotten orientation, which contains the initial marking, M0. Yeah? And this will be our graph Gn. And we put back the orientation, okay? And now, in one safe Petri net, there is a standard way to define which transitions are independent. And 2 transitions are independent if they satisfy this relation. Yeah? Okay, and now we define the complex in the following way. We define a 2-dimensional cube complex. We can define more cubes if we want, but 2-dimensional is the most important part. So the 2-dimensional cube complex has the 0 cubes and the 1 cubes of this complex x of n are the vertices and the edges of the graph G of n as I defined above. And now, which 4 cycles in this graph we should take in the complex? A 4 cycle in the graph defined by 4 markings define a square in the complex x of n, if and only if there exists a pair AB in I, such that the edges, the arcs of this square, of these 4 cycles are labeled in this way. This is, the picture is like this. You put a square you put a square in the complex if and only if the arcs are labeled AB, AB, and the pair AB is in the independence relation defined by the Petri net. And then what we prove is that this complex X of n oriented, directed, is a finite directed special cube complex. And the labeling lambda which to edge which each arc of this of the graph of this complex associate the transition allowing to go from one marking to another one. These are the labeling. And in fact, this is a labeling of the complex with a trace labeling. So it's this is theorem 2. And now I have to formulate the main result. So we proved that, but after theorem 2, we proved that if we have xn, the universal cover of xn, then this is a cut-zero cube complex, which has for which the filters have nice regular nice labelings. They are. But we take not all filters. Now it's important that we take the filters defined by the pre-images of the initial marking M0. So maybe I have to draw in the following way. So we have this is x of n, and this is x of n, and this is the initial marking M0. And this is a big object. This is a universal cover of x of n. And you have M0 tilde many times, an infinite number of times. And then what we do, we take a principal filter of one such pre-image. And this is a domain of an event structure. And we denote this event structure. In fact, they will be all isomorphic. The event structure of x of n. This is the event structure of x of n. Yeah. And this event structure, in fact, is labeled. It has trace labeling and has a precedence and a conflict relation. Okay, this is one. And then the second event structure is that which I define in a very fuzzy way, is the event structure of the unfolding. So we have an event structure which comes from the universal cover of the special cube complex of one safe Petri net, and the second comes from the unfolding. And our main result say that the two event structures are isomorphic. The two are isomorphic. And to prove this, we really have to define what is the event structure of unfolding. And this was done by Nielsen, Plotkin, and Winskell in their paper from '81, which is very nice. It's first, suppose that you have a trace alphabet, and you take a finite word in this alphabet, and last of sigma is just the last letter in the word. Okay? And now, if you have a trace alphabet, then you have a kind of binary relation between the words. And namely, if you have two words, sigma and sigma prime, and you have a pair of letters which are in independence relation I, A, B, and I, then the words sigma A, B, sigma prime commute, or are equivalent with the word sigma B, A, sigma prime. This is mean that A and B commute, the independence relation that I can exchange, yeah? And this gives you the traces. What are the traces? The traces are the equivalence classes of this relation one, of this relation. They are also called Mazurkevich traces, but okay. And what are the prime traces? The prime traces are the traces for which any word ends in the same letter. All words in this trace has the same last letter. This is prime trace. And then there is a notion of inclusion, which will give us the precedence relation. Is here, I will not specify it. And then this is the result of Nielsen-Plotkin-Winskell, saying that if you take a triplet such that E is a set of prime firing tracings over one safe Petri net, small o equal, the precedence relation is a previous relation which I don't specify, restricted to the traces, to the prime traces. And the conflict is between two traces are in conflict if there does not exist the third trace for which you have such property. And if you associate lambda, you label each trace by the last letter. This is trace labeled event structure. And this is called the unfolding of the one safe Petri net. Yep. And what we proved, in fact, this should be E of n. What we proved, this theorem is saying that, I forgot a lot of definitions. Okay, this is good. I skipped a lot of definitions, but so we proved this, that the two event structures coming from different objects are the same. So I skipped a few definitions, but okay. Prime firing tracings are you take, okay, just I defined the prime traces, and then this was a general definition, but if I look now one safe Petri net, I have the independence alphabet as defined above, and with respect to this independence alphabet, I have the words are the firing sequences, and with this independence alphabet, I consider the prime firing traces, and they are the events of the unfolding in Nielsen and Plotkin. And I will not give how much I have. Should finish.
5 minutes.
5 minutes, okay. I will not give the idea of the proof, but in the proof, really it's very nice because we consider geodesic words in a median graph in a domain, and in fact we prove that if you take the two geodesics between two ends, between V0 and some vertex in the configuration, then all such geodesic define a trace, the same trace, and this is exactly one trace. And then we transfer the precedence relation and the conflict relation in the language of median graphs, and this is just, for example, the two geodesic traces are in conflict. If and only if you don't have, if and only if they come from two vertices U and V, such that there does not exist a W, a vertex W, so that U and V belong to the interval between V0 and W, and the interval is a set of all shortest paths from V0 to V. And then there is also notion of prime trace, and the trace is prime if and only if the interval between V0 and V, geodesic trace is prime if the interval between V0 and V ends just with one edge. It's like this. And it is exactly when you make the gate of V0 on the hull space containing V, defined by the theta class of this edge, So you have a geometric redefinition of all notions of precedence, conflict, prime trace in the language of the domain. And in fact, we proved that in fact the prime traces correspond to the hyperplane of the domain. This is one thing. And then second, we proved that the precedence relation defined for one safe Petri nets correspond to this precedence of hyperplanes, and then also conflict, and then we get the result. Okay, I promised some applications. Applications, this should be the subject of another talk. In fact, we can, when you have this result, this bijection between one safe Petri nets and the special cube complexes, you can take care of the special cube complex. You can forget a little bit about one safe Petri net sometime. And for example, if you want to construct example or counterexample, you just take universal cover of the special cube complex and get results. In fact, we proved the following things, that the event structure we call the hyperbolic if its domain is a principal filter of a Gromov hyperbolic domain. What is Gromov hyperbolic in case of cat-zero cube complexes is equivalent that your grids are uniformly bounded. You don't have larger and larger grids, or you don't have an infinite grid. Yeah? So this is a hyperbolic domain. And we don't know whether this satisfies Thiagarajan conjecture, but then we call an event structure strongly hyperbolic if, in fact, its domain is a principal filter coming from the universal cover of a finite non-positively curved complex. And in fact, for them, this is the Thiagarajan conjecture is true. And why is true? Because Agol, this is a very hard result, so proved that if you have a finite non-positively curved complex such that its universal cover is hyperbolic, then this complex has a cover which is special. And therefore, we can apply our theorem for this cover, finite cover, special finite cover. And therefore, we have this result. And in fact, we use this theorem for, and to produce a counterexample to another conjecture by Thiagarajan about MSO decidability of logics of event structure. MSO of unfolding, event structure unfolding. This is, in which way we produce a counterexample? In fact, we considered a square complex, which is not special but has a finite cover, and was universal cover is hyperbolic. Therefore, theorem 4 applies for this complex. But it is not context free, and it is not of finite tree widths. And in fact, we proved that the MSO logic, not of the event structure, but of the domain, of the configuration of a domain of an event structure, is MSO decidable if and only if the domain is context free, and this is if and only if the domain has finite tree widths. And our counterexample is hyperbolic. Therefore, you apply theorem 4. It comes from one safe Petri net. It is not a finite tree widths. Therefore, MSO for this domain doesn't apply. But to get for events, that what we do, we hair the domain. We take in the domain and we put one hair on this, and then when you get that MSO now not for configuration but for events is not decidable because it was not decidable before for the domain, for the configuration of the domain. And this trick allows to show a counterexample to the third Thiagarajan conjecture. And okay, I have open questions, but maybe I stop. You can ask me about the open questions. Okay, thank you.
Are there any questions?
Non.
In English or French?
En français, ça va. Oui.
Merci Victor. Super exposé. Antipédagogie peut-être, mais...
Antipédagogie, c'est ça le principe.
C'était très intéressant. Donc là, tu nous as montré une application qui est encore montrée qu'une autre conjecture de Thiagarajan était fausse. Est-ce qu'il y a des applications plus positives, c'est-à-dire que tu montrerais grâce à cette injection qu'il y a des trucs faisables dans les conjectures?
Oui, mais les gens de votre domaine, ils ont la mauvaise habitude de ne pas formuler des questions ouvertes. Thiagarajan, il a formulé 3 conjectures qui étaient tous les 3, on a montré qu'elles sont fausses. Et on a plein d'exemples qui sont corrects. Mais je pense que ces conjectures étaient très belles. Parce que entre fini et infini, entre borné et non borné, etc., c'est logique, décidabilité, non. Ça. ouais, on a des exemples où ça marche, mais on n'a pas de problème qui peut résoudre. Donc, sauf négatif. C'est vrai. Who publish negative results? Vous connaissez la blague.
Est-ce qu'il y a des questions algorithmiques sur du côté des
En effet, il a des.
Est-ce qu'il y a des questions algorithmiques sur ces...
Non, on a plutôt des questions de décidabilité, et c'est ça les conjectures. In fact, oui, nous on pense que hyperbolique satisfait, mais c'est la deuxième conjecture. Nous on pense qu'en effet, si on a un complexe de courbure non positive, NPC, fini, il n'y a pas d'algorithme qui décide si dans son revêtement, le filtre, il y a un nice label, regular nice labeling. Donc, ça, on pense que c'est non décidable, c'est ça. Strongly regular, qu'elle vient de revêtement de quelque chose fini. Deuxième, c'était nous on l'a formulé aussi, mais ensuite on a vu que c'est Agol, il l'a formulé. Il dit qu'il n'existe pas d'algorithme que si on a un complexe NPC fini, s'il y a un revêtement fini spécial. Ça, c'est des questions de décidabilité, ce n'est pas vraiment algorithmique. Mais peut-être ici qu'il y a des choses plus positives. Par exemple, ça c'est une jolie question aussi du type, on a un complexe MPC fini, est-ce que son revêtement est hyperbolique, qui n'a pas de grille? Non, tous les grilles sont bornées. Peut-être ça c'est positif. Et deuxième, est-ce que son tree width est fini? Donc c'est vraiment une question que on a un objet fini, on a un revêtement qui est infini, et on peut se poser de façon légitime la question sur cet objet fini. Est-ce qu'il est comme ça ou comme ça? Et là, peut-être s'il a des réponses oui, il y aura des algorithmes aussi, questions algorithmiques. Context free, en effet, c'est équivalent à tree width. Ça, on a démontré. Mais après, je ne sais pas, toi, tu es spécialiste du domaine. Dis, quelles questions algorithmiques? Oui, moi.
Après, reconnaître les trucs spéciaux et tout ça, c'est facile.
Oui, ça c'est. Dès qu'il est fini, c'est facile, oui, c'est les hyperplanes.
On peut faire quelque chose de un revêtement fini. Okay, donc, le fini peut être arbitrairement grand.
Oui, on n'a pas réfléchi, mais on n'est pas spécialiste du tout du domaine. C'est pas.
Il y a d'autres questions? J'ai pas tout suivi.
Désolé.
Mais, non, mais pas de souci. Mais donc là, vous avez des caractérisations des structures d'événements qu'on obtient en dépliant des réseaux de Petri OneSafe.
Oui.
Mais la caractérisation est en termes de propriétés un peu géométriques du domaine de configuration.
Pas du domaine, mais
Enfin, ouais, du complexe.
du complexe. Ça veut dire que si on a un réseau de Petri OneSafe, on a défini le complexe des carrés, comme on l'a défini, et on prend les revêtements, on prend un filtre de...
Du coup, ma question, c'est est-ce qu'il y a moyen de visualiser en fait cette caractérisation du côté des structures d'événements, c'est-à-dire de décrire en termes peut-être plus concrets sur la structure d'événements, à quoi ça correspond parce que moi, mon intuition est plus dans le monde des structures d'événements. Est-ce qu'il y a quelque chose à dire ou est-ce qu'il faut vraiment construire le complexe de cubes?
Ouais, pour nous, tous les trucs qu'on a fait, c'était vraiment, on travaille sur les domaines. Et je sais, par exemple, si on a 100 conflits, ça c'est des domaines distributifs. Ça c'est des caractérisations comme ça. Je sais qu'il y a des classes aussi des structures d'événements. Mais caractériser en termes de structure d'événements, oui, c'est donner une axiomatique par structure d'événements, ça sera intéressant, mais est-ce que ça sera possible? Est-ce que ça sera possible? Parce que d'une certaine façon, c'est assez général, toutes ces choses-là. Donc, avoir des actions simples, ça va restreindre à beaucoup. Et si ce truc de conjecture sur les hyperboliques que j'avais, en effet, les hyperboliques, ça c'est des bordels locaux. et des régularités globales. C'est ça, la hyperbolicité au sens de Gromov. Localement, on peut avoir plein de choses mauvaises, mais globalement, il n'y a pas de grille. Et c'est ça qui peut être peut-être un obstacle. Oui. Ah, c'est bien de reconnaître. Ça, oui.
Si j'ai bien compris, donc les complexes 4.0, c'est un sous-ensemble des complexes cubiques spéciaux.
Oui, c'est exactement les revêtements universels des complexes cubiques NPC finis. Non, c'est pas exact. Non, c'est pas vrai. Non, je dis des bêtises. Là, il y a, en effet, il y a des complexes 4.0 qui ne viennent pas des revêtements finis. Ça, c'est sûr. Non, on ne peut pas complètement les comparer. Parce qu'ici, c'est fini. Mais si ce n'est pas fini, c'est vrai. On peut dire que ça, c'est vrai. Si ce n'est pas fini. Ce n'est pas les revêtements des choses finies. C'est tous les trucs qui sont dans les finis. C'est ça.
Un squelette des complexes cubiques 4.0, c'est les graphes médians.
Oui.
Un squelette des cubiques spéciaux,
On ne sait pas. Ouais. Je ne pense pas que c'est sauf la caractérisation qu'ils ont donnée. Je ne pense pas qu'il y a quelque chose de très structurel à donner.
Oui, la question, c'est une question naïve. Tout ça, ça marche sur OneSafe. Qu'est-ce qui se passe est-ce qu'il y a encore quelque chose à faire?
Je pense qu'il y a des choses à faire. Et même, moi, mon rêve, comme je suis nul dans tous les trucs de concurrence, ça c'est bien, quelquefois, d'être nul. Moi, je pense qu'en concurrence, où on a l'alphabet de traces, est-ce qu'il existe des alphabets de traces que ce n'est pas deux lettres, A et B commutent? Mais ça, c'est les relations dans les groupes. Il y a un mot qu'on peut les remplacer par un autre. Et ça correspond dans les domaines qu'il y a un chemin qu'on remplace par un autre. C'est les homotopies qui définissent cette truc de... Mais sinon, oui, ça c'est de très bonnes questions. Ouais.
Si tu essayes de généraliser ce qui se fait par exemple, deux safes, ce qui se passe, c'est que quand tu as des jetons dans une classe, c'est pas trop d'où ils viennent. Donc, tu peux faire du bazar, tu peux faire des choses où de temps en temps tu peux faire A et B, parce qu'il y a 7 jetons, mais peut-être après tu as enlevé un jeton. Et du coup, donc, des fois ils sont tous les deux activables, des fois ils sont pas tous les deux activables.
Peut-être c'est là
Ça dépend pas, et c'est pas un truc structurel, ça dépend du chemin que tu as pris pour arriver. Donc ça casse un peu cette histoire on a un alphabet avec une relation dessus, un peu indépendante de la machine qu'il y a derrière, des relations de dépendance. Donc il y a Rémi Morin qui a fait des trucs sur les automates de traces un peu généraux avec des choses comme ça, donc
ouais, je pense qu'il y a des questions et peut-être il faut mettre des conditions de plus pour avoir quelque chose de structurel. Nous, on veut avoir des beaux domaines sur lesquels on peut travailler. Mais des beaux domaines, ça signifie que peut-être ils sont difficiles aussi. Ok.
Merci. On peut encore remercier Victor.
Merci.